Okay, I will talk today about exploring volcanic signals with DAS and also some geophone signals. How do I change slides? Okay, 1 second. Okay, perfect. Yes, so a quick outline for my talk. I will briefly introduce the 9N seismic network. Then I will explain a bit about the theory of coherence-based detection methods. Then we will look at some array seismograms for various volcanic signals. And then I will go into a bit about the effects of downsampling, and especially the question, do we need all that data, all that DAS data for detection purposes? And the answer is yes, but not all the data. And then we also explore template matching on DAS signals. So a quick overview of the 9N network. It was a temporary network installed for 2 weeks at Mount Etna. I highlighted the different craters at Etna, and especially the north-south-east crater, because there we will look at some explosions. In total, it's like a 1.5 kilometer long cable with 2-meter channel spacing, and there are also 15 geophones. But you can see that the aperture of the array, it's not ideal to detect the signals, but we will explore that in a moment. So just in general, to follow like the theory of the coherence-based methods, up there is the formula for signal coherence. So it's an estimation of how coherent 2 different signals are, and it's computed by taking a time window, computing first the cross-spectral density between 2 signals, and then normalizing them by the autospectral densities. And this gives a normalized covariance, which is bounded between 0 and 1. So here's just a brief example to highlight the methodology. We have a signal, and we can see a clear event. So we just take 2 windows. One contains this event, and the other one contains noise. And then we compute the signal coherences between all the channels. So between the first channel and the second, and the first and the last, and all other combinations. And we assemble them in a matrix. So this is done here, and we can already see that for the signal, we have a coherence between a lot of channels, because there's a strong coherent signal, while for the noise, we don't have. And then we can do some further processing, in this case, an eigendecomposition of this matrix, which will give us eigenvectors and the eigenvalue spectrum. And so this method already exists. From this eigenvalue distribution, we can do some inference if we have dominant sources. So if we have a few strong eigenvalues, this means that there are a few strong dominant sources, while if we have a more flat eigenvalue distribution, it means that we have more equilibrated sources or no sources. And we can do this procedure for each time frequency bin, so we end up with a kind of spectrogram. So this would be the example for this event. And we see that it's a bit broad, because in the computation of the windows, we do some averaging. So we have a limited time resolution. And in the case for this data, we have a lot of signals. So we actually go down almost to the theoretical limit, which is still stable. But I will show the results in a second. And we can use this array covariance or coherence matrix in a different way to detect events. And the first one would be to look at the spectral width, which is, describes the skewness of the eigenvalue distribution. So if we have low values, it means that we have dominant sources. But we can also do some other approaches. So we could look at the eigenvectors which belong to these eigenvalues. And for example, if we look at the first eigenvector, it should correspond to the strongest source. And we could try to cluster that or use it as a kind of matched filter. So here's an example of the DAS data and a so-called array spectrogram. So computing the spectral width at each frequency time bin. And which is really nice, we get for this DAS record, which is half an hour and quite a lot of data, we get one single spectrogram. But the energy in the spectrogram is only coherent energy. So it's a really strong filter which filters out noise, and especially for DAS, we are used to very noisy data. And we can see, for example, here we have some degassing events, so they're in the frequency range between 1 to 12 hertz. And then over here we have some anthropogenic, really high frequency events, and this is also captured in the array spectrogram. And here I'll just show some examples for some of the signals we have in the data. For example, on the left side is a volcanic explosion, and we have, I plotted up to 100 hertz, but it goes even higher, and we have, at all frequencies, we have really strong coherent energy. And on the right side is a volcanotectonic earthquake, and we see that the energy is mostly between 5 to 30 hertz. Here are a few more examples. This is now taken from the geophones, not from the DAS, because unfortunately the DAS was only functioning 20% of the time. So here are some more explosion, and also some of them are listed by the INGW. And here are also some more volcanotectonic earthquake. So unfortunately we don't have all of them on DAS. So I just showed that. So the easiest, like the very most basic method to do some kind of detection would just be to take this array spectrogram, do an averaging over frequency, and then we end up with the curve. For example, the middle plot shows the average between 8 to 14 hertz. And then we can just set a cutoff threshold, and we say everything that's below, we treat that as a detection. And yes, we can do that for different frequency bands, and this would be like the very most basic method to take such an array spectrogram and do a detection out of it. So this method has been used before for volcanic tremors. So usually people take very, very long time windows on the order of hours. And also just for a few stations, so for example with arrays of maximum of 15 stations, because it has a limitation, since we compute the signal coherence between all channel pairs, we basically end up with very large matrices if we do this for DAS, because we have hundreds, thousands of channels, so we get matrices up to 1 million entries, and we have to decompose them, and this we have to do for every time frequency bin, so this can be quite computationally heavy. And also, we go to really, really low temporal resolutions of down to average windows of 40 seconds. So one of the questions, so yes, here is just an example that you get like quadratic cost for the number of stations compared to the time it takes to run this algorithm. And this is not really surprising because we have to eigendecompose all of these matrices. So one question we had is, do we need all this data for detecting events? Do we need every single dust channel to be able to detect events? And so the first thing we explored was to take these averages of the spectrograms and compare them for different downsampling factors. But if you do this, you see that all of these lines, they are shifted by a factor. And they are actually quite hard to compare because they're offset. And we were asking us why this is the case. And luckily, in the ocean acoustics, they already did some theoretical work based on microphone data or hydrophone data for linear arrays. And so here is shown that they explore different spacings between the sensors and also different ratio between the number of stations and the number of snapshots you have to compute the eigenvalue distribution. So these are eigenvalue distributions, and we can see that they change quite dramatically when we change the spacing of the sensors. And what we do when we just take a DAS cable and we downsample is we do two things. First of all, we increase the spacing of the sensors. So all of a sudden, if we downsample by a factor of 2, we don't have a channel spacing of 2, but of 4. And secondly, for these algorithms, we also change the number of stations because we go down with the number of stations, and then we have a different ratio between the number of stations to the number of snapshots. So this is basically the theory from simulations, and we did a test on a linear section of the cable to test if that's also the case for seismic signals. So we take this from channel 240 to 400. We have a linear section of the cable, and we make sure that we always take 40 channels, so we don't change the number of channels and the number of snapshots. They stay constant, and we only change the channel spacing. And what we see if we look at the eigenvalue distributions is that we have an effect if we increase the spacing. So if we downsample, we increase the spacing. We increase this ratio of the spacing divided by the wavelength. And another effect is when we change frequency, because then we decrease the wavelength, and we decrease beta, and we also increase the spectral width. So as you can see, if we go from the top left, where we have the spacing of 2 meters, and we look at 2.5 hertz, and then we increase the frequency, then we will get a broader eigenvalue distribution. So this also explains quite nicely, if we look at the array spectrograms, why there are very, very low values for low frequencies and high value for high frequencies. And actually, we can even make sure that we leave these parameters constant by looking at the dispersion or the velocity, and really make sure that we keep the beta value constant. And then we see that actually in these how do you say, symmetric entries of this plot, we get extremely similar results. So for example, these two, because we changed the channel spacing, but we also changed the frequency. So we keep the ratio of the station spacing to the wavelength that we look at the same. Nevertheless, so this means that we could, in theory, compare these lines, which are here these average spectral means, when we normalize for each frequency, because we say actually maybe it doesn't mean that we have more coherent energy in one frequency range, but it's because of the channel spacing, because we changed the frequency. And so these two lines is one time in blue, it's the original undownsampled data, the full data set, and in orange is downsampled by a factor of 20, so that you can see the difference. So the original data is performing better, and in the top plot I plotted on the y-axis, you can see the downsampling factor, and then the color would indicate if the detection significance improves. So what we can see is that for events, which are indicated by low spectral width values, we see that for large downsampling factors, we get a decrease in the detection significance, which we would expect. But we also see that in the very top, it's a ratio of 1. So if we downsample by a factor of 3, 5, we actually performing not worse. And this is huge because since the computation is quadratic, going down by a factor of 5 will speed up the computation significantly. And before we go on, I just wanted to briefly mention the other two directions that I'm looking at for detecting events. And one of them is to take the first eigenvector, which should, in theory, correspond to the strongest source, and do some kind of clustering, or in this case, I just computed the cross-correlation between all these complex eigenvectors. And in the time windows shown here, there are 3 explosions, and if we look at low frequencies, or we see that for all, but especially for low frequencies, these 3 explosions, they don't have a good correlation with the other time windows, but the time windows themselves have a really large coherence. This changes a bit if we go at higher frequencies. So if we look at the frequency band from 8 to 14 Hertz, we actually see that the general cross-correlation between all the eigenvectors is quite low. But if we look at the explosions, between themselves, they have a strong cross-correlation. This works especially well for explosions because we also have a coupling of the, like all the signals come from the same direction, but for explosions we also have a strong coupling between the acoustic and the seismic waves. So we actually see a different imprint on the first eigenvalue. And another thing we can do, so here is an example where we look at low frequency events. So this is filtered between 0.1 to 10 Hertz, and this is between 0.1 and 0.6. And here, this is more dominated by degassing events. So these events here or here, they are degassing events, and you can also see that they have low spectral width values at high frequencies, or around 10 Hertz. But then we also have these interesting pulses at very low frequencies, below 1 Hertz. And these are short tremor pulses. And they are quite visible in the low frequencies of the spectral width plot. And in this example, I took the first eigenvalues of a few of these events and used them as a kind of template. So I did the cross correlation between the templates of the STP we had, and then we can see that it actually quite accurately detects all these short tremor pulses here, which are different. You cannot see them really if you also look at the higher frequencies. So to verify also a bit the results we got from the downsampling of the dust data with the spectral width method, we also looked at template matching. And for this, I took a degassing event. So on the right side, you can see 1 hour of data. Here it's around 9 minutes. So I took these two templates, one for the dust and one for the geophone. And the event it doesn't have a really large signal-to-noise ratio, but still the results we get are quite impressive. So on the left is shown for 2 hours of data. So even in these 2 hours, we already get a significant amount of detections. And what we see is that the black line shows 10 times the medium amplitude deviation. So for the DAS, this is lower than for the geophones. And also these peaks are higher in comparison to the median amplitude deviation. So this is also a bit demonstrated in this plot here. So you can see that the geophones have a quite larger medium amplitude deviation. And we can also quantify that. So this is just a brief summary of 9 hours of data, which the DAS were active during that degassing episode. And we get 70 more detections with the DAS. And the reason is that we have quite a lower medium amplitude deviation, which is not surprising because we have many more sensors. And this means that the ratio, so this would be the ratio of one of these peaks compared to the medium amplitude deviation, is also significantly higher for the strongest events. So I investigated how we would actually detect events if we would downsampling the DAS and do the template matching each time. And what we see is that for the first, like for a downsampling factor up to 5, we don't do any worse. We have the same amount of detections, and then we start to decrease. And this is also a bit signified here by the plot of the medium amplitude deviation. So it stays the same up to a downsampling factor of 5, and then it increases rapidly. And an explanation for this would be that if we have very, very dense channel spacing, we have some correlated noise. So if we start to stack all of the cross correlations and we kill the noise, if we go below a certain channel spacing, then actually we won't improve anymore. And also for DAS, inherently, if we have a channel spacing of 2 meters and a Gaussian length of 10 meters, then some of the data is by computation already a bit redundant. And this is, the template matching can give quite some interesting results. And this is also a bit a point Goja made yesterday, but a bit more sophisticated. So here I have 2 cross-correlation time series. The top one is for explosions, and the bottom one is for degassing, like one of the degassing templates. And what we can see is that the degassing is really strong. It has a lot of detections. And when we have these large explosions, we get a time period where they completely die off. So also the day before, there were constantly these degassing events, and then they abruptly stop. And these are the hours before the explosion. So 2 hours before, 1 hour before here is the explosion. And we see that we have all these strong degassing events. But what we would not see is that actually also after the explosion, we have a lot of degassing events. And if we would just count the events, then we would miss that there might be some relation between them. So here are my main takeaway questions that you can hopefully take away from this talk. And the first one is, for event detection purposes, we can possibly reduce the data volume significantly without missing events. And this is important because we have less computation, but also less storage. We already heard that storage can be a significant problem, especially for DAS. I won't claim this for all DAS applications. So in some cases, we really are interested in having a really dense spatial sampling. But especially for volcanic event detections, we don't need all this data. And the second one is that template matching on DAS is very powerful. And surprisingly, it's really rarely done. And one of the main reasons is that we need good templates in advance. And so this is also where the spectral width method can come into play, because we already get a nice overview of the signals that are in the data set as an early data exploration, and then can use them directly as input for template matching. So here also all the references that I referred to in the talk, and thank you all for your attention.